Hello students. So in the last class, that is in the fifth class, okay, so we started with the cyclopentadienyl. Okay, so very important, pentadienyl. Okay, so it is also represented as CP in most of the textbooks. Okay, and today in the class sixth, so today is a class sixth year. So in order to understand all the concept, you have to go through all from video 1 to video 6 continuously. Okay, from 1 to 6, 7, 8, 9, 10. So this is the classes, so then only you can understand. Directly switching on to any of the video and then you will not get the proper points to learn more, to learn correctly, is it? So always have the sequence properly and make a point of the points what I am discussing here. So in the last class we started with the cyclopentadienyl. So that is not that is your this type of molecule. Okay, so like this cyclopentadienyl, and if you see the diamagnetic complexes, that is neta 5 we represent here, cyclopentadienyl. And if you see the diamagnetic type of complexes, okay, so like ferrocene, metallocene we call it. So we will learn more about this ferrocene, metallocene. So they show the resonance. Okay, they usually show the resonance from the proton NMR. Okay, so because of the protons, proton NMR, they show resonance here. And the spectrum will be at the around the range of 3.5 to 5.5 delta. Okay, this is a delta is a NMR scale here, from 3.5 to 5.5 range. Usually they show this type of diamagnetic type of metallocenes or neta 5 cyclopentadiene complexes, and this resembles usually aromatic in nature. Okay, so usually benzene and all the protons, they show in this range. Okay, and that's why the ferrocene is said to be very good aromatic in nature because of this proton NMR. And if you see one more thing fascinating here is if neta 1 complex, this is about neta 5 cyclopentadienyl. If you go for neta 1 cyclopentadienyl, like in yesterday's class we have learned, where this is attached to one of the only carbon 1 here. So you can see here the metal is attached to only carbon 1 here with some of the ligands here. Okay, so this is called neta 1 cyclopentadienyl, and in this case if you see the NMR here, so it is more complex in nature. Okay, so this is very complex in nature. And if you see the NMR here, so in this case there is will be two regions, the two ways here, alpha hydrogen, and it appears about around 3.5 delta. Okay, alpha hydrogen appears around 3.5 delta, but gamma and beta hydrogens, okay, if you see they occur at 3 to 7 delta. So like this, so there is a complication here, not like simple like here, it changes here. So for if you see the alpha hydrogens, it's going to show at 3.5 delta. If you see the gamma or beta alpha or beta hydrogens, so you can see it is showing in the range of resonance will be in the range of 5 to 7 delta. So this is what about the one nature we call for why this shows this, because of fluxional behavior. Okay, fluxional, fluxional behavior of the molecule. Fluxional means there is the metal is rapidly moving. So here whatever the metal is there here, so it is rapidly moving from C1 to C2, then C3, C4, C5. It is not in a fixed case here. Okay, so that we call it as a functional behavior. So where in which we can see that rapidly the metal is rapidly moves around the ring here, so like this. Okay, and it make all the protons equivalent, and when it moves here, so what will happen, as the metal moves here, so proton, whatever the protons will be in each of the carbon, what we are seeing here, so there seems to be as equivalent proton, this seems to be as a equivalent proton. So that we call it as a fluxional behavior. Okay, that we call it as a fluxional behavior of a molecule. So this neta 1 is going to show, and that's why the NMR study is a very complicated study in this neta 1 cyclopentadienyl complexes. Okay, now if you see the molecular orbital of this cyclopentadienyl, so one by one if I go, so simple, you can go like this here as a like this energy psi 1, psi 2, psi 3, psi 4. So if I go for the psi 1, as you know that very first one is very simple, so I can write it as a plus here. And if I go for, if you want to show with aromatic with orbitals here, so you can show in this way also. So one I will show, others you can try it. Okay, so like this, and all the side there will be plus 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 like this. So this is called your psi 1. So here what will happen, energy is very low. If you see psi 2 I can go for like this psi 2 and psi 3. Okay, so if I take the cyclopentadienyl, one node is going to happen here. So this is plus and this is minus, you can show this is psi 2, and psi 3 if I want to put, I will go for with this like this psi 3, and I will put like this is as a plus and this is one minus. So this is what I can go for 2 here, psi 2 and psi 3. So this is psi 2 and this is psi 3. So where you can see one node is there. Okay, so this one node or this one node. Then if you want to go for psi 4 psi 5, two nodes you have to generate. I will write here two nodes like this. You can do cyclopentadiene here, and you can generate one node here and one node like this. So here plus minus minus plus. So this is one psi 4 and psi 5 if you want to show. So again you can generate the so like this also. Okay, so you can generate the two nodes in this way. So you can write here plus minus, or here you can write minus minus plus plus like this. Okay, plus plus and minus minus. So like this we have generated the molecular orbitals of cyclopentadienyl. So psi 1 psi 2 psi 3 psi 4 psi 5. So this all represents what your lobes like this. Okay, so this is how in one case I have done. So you can generate here in this all the cases. Okay, so plus means what, minus means what, upper side is plus. So upper side you can write here all plus like this orbital, you can write here plus orbital, here you can plus. Down one is minus, you can write here minus, you can write here minus like this. So this will generate your one node. So like this you can draw for all the things. So first, that's why I have very easy way I have taken you the nodes, then the orbitals you can draw and make it easy. Okay, then how does the orbitals now these are the molecular orbitals, and when I go for the overlapping now, so this is very much important. So overlapping with the metal orbitals, one I will tell you, others thing you can mention. Okay, or you can do the same way. Now if I take for the psi 2 only, so psi 2 if I remove here, so one diagram I can make it here like this. Okay, so one node I can put it here like this. So this is one, this is one. If I put here, this is one plus I will take it here, and minus, and here I will take it as a minus in this way. Okay, this is one condition I have taken of psi 2 here. Okay, plus plus is there, minus minus is there, one node is I have generated here. Now if I want to now take psi 2, if I want to now overlap with the metal, so it has to be, if I take this axis now like this, x and y and z here. So if I take here x, y and z axis, so which axis, which metal, which orbital of the metal is going to overlap exactly to this. So plus, so I will draw here itself. So if I draw this like this axis here of the metal here, so like this. Okay, y, so I think dyz. So if I take this like this, dyz here plus, and here if I take in this way, so here minus is there, so minus plus minus plus. So this if you see here, so this is what dyz. If I take this orbital dyz, I can overlap it properly here. See here minus is there, here I can put, if I take it and overlap here, so I can overlap here minus to minus and plus to plus in this way if I remove and overlap here. So this orbital is a best suitable orbital for overlapping this orbital. So like this. Now if you take this orbital, so all the sides are totally, so s orbital is very good here. So s orbital has all this one so it is going to overlap. Okay, 4s orbital, so easily you can overlap, or dz orbital, so dz square orbital also you can overlap. Okay, 3d z square orbital also you can overlap here like this. Okay, so all are plus here, so here also is plus plus will be there, so you can overlap it here like this. Okay, so easily, so like this you have to judge which orbital can be overlapped into this, and you have to see that this is how the structure and bonding of the ferrocene molecules would be generated. So this is about the molecular orbital, and this is how I can the overlap, one overlap I have shown you. So like this you have to see the structures of the molecular orbitals of each metal as well as the ligand, and you have to try to overlap that. Okay, and that's why in psi 1 psi 2 psi 3 you can see overlap is okay, because as the nodes goes increasing, the overlap becomes difficult. Okay, so this is what we have to observe. Now if you see this molecular orbital, okay, of the cyclopentadiene, that is C5H5, since there are 5p orbitals on the carbon. Okay, so of carbon, because like this we write it here, 5p orbitals of the carbon. So what will happen here, so it is we are generating how many, 5 molecular orbitals. This thing you have to like in the we have just shown it here. uh, behind I have shown you. So 5 molecular orbitals are generated, and the most important overlap, as I said now, just it is psi 1. Okay, the most important overlap is a psi 1, and which is that dz square. This orbital is very much important. And psi 2, psi 3, as I shown behind, psi 2 and psi 3. So best overlap of the metal orbital is xz and yz. Okay, so this is what dxz and dyz orbital. So this can overlap very nicely with psi 2 and psi 3. So exact this will be there. And if you consider psi 4 and psi 5, okay, so this orbital, they are having very high energy because of the nodes, increasing nodes here, and they do not interact very strongly with metals now. So they are not going to interact very nicely with the metal orbitals. And the cyclopentadiene group is therefore we say it's not a good pi acceptor, and that's why the cyclopentadienyl CP, we say it's not a good pi acceptor. Okay, it's not a good pi acceptor. This is the reason why it is not a cyclopentadienyl is not a good pi acceptor, because it fails to overlap properly with the C4 C5, and it cannot accept the proper electrons from the metal here. So no proper overlapping, and that's why it does not accept behave as a good pi acceptor here. So cyclopentadienyl, so that's why generally they are basic. Okay, so that's why the cyclopentadienyl becomes generally basic in nature, and they encourages the back donation from the metal. So, and this basic nature, that what happens, this encourages the metal for back donation. Okay, for the back donation from the metal to other ligands. That is very much important, to the other ligands. Okay, since they are basic in nature, it helps this metal to back donate the electrons for the other ligands. So this is a fascinating part of the cyclopentadienyl. This thing you have to keep in the tricky thing you have to keep in the mind. Now if we put the two cyclopentadiene, what will happen? Now this is of the one cyclopentadienyl. Now that's what ferrocene had said. Now I have taken the two cyclopentadiene. This is one cyclopentadienyl and another cyclopentadienyl. If I put it here in this way, okay, and in between iron or any metal, if I put like this, so what is happening here? So it is called as metallocene. So such side of this we call it as a metallocene. Don't forget this. Okay, so this is called now as a metallocene. Okay, so if I go for this now molecular orbital of this metallocene, now two metallocenes. So first if I go for this, very simple. Okay, so anything you can put it from this molecular orbital. Now just see here. So if I put here psi 1 here, so this is psi 1. Okay, psi 2, psi 3, I will go for here sideways. Psi 2, psi 3, 1 2 3 4, psi 3, then this is psi 4, psi 5, 1 2 3 4. So these are the molecular orbital of the ligand, and here I will take it as a of the metal. 1 2 3 4 5, that is your 3D. Okay, and then it comes 4s here, and here I will take it as a 4p, 4p, this way. Okay, so this is a molecular orbital of any of the metallocene or the cyclopentadiene. And if I go for this, what will happen now? This we can write it here like this. So this two I'm going to put here, and this also is going to put 1 2 3 4 this way. So this one, now here is very much important. So this what metal is there, no? So it will split into 1 2 non-bonding like this, 3, then here it will be 4 and 5. So this is very much important. This part is very much important for the bonding like this. Okay, 3D orbitals, so like this. So this is, and like this you can put it here. Okay, and this all goes up here like this, then like this, then this also will go up here like this. So this becomes the molecular orbital diagram for any of the metallocenes. Okay, so like this you can put, this is a metal and this is of the cyclopentadiene here. Okay, now if you see whatever the electrons will be there, for example if I take the iron here, so scandium, titanium, vanadium, chromium, manganese, iron, 6 7 8 electrons. Now filling takes place here, so 2 3 4 5 6, okay, 2 3 4 5 6 7 8. So like this, and that's why ferrocene will be the diamagnetic in nature. So since there is no no electrons paired unpaired left here, so it is diamagnetic nature. So whatever the now iron is over, then whatever 8 group elements will be there, then that's why they are all diamagnetic and not so much reactive here because of diamagnetic nature. But if you go for vanadium or ninth group or some other groups, so you can see that there will be the paramagnetic nature will be generated here. You try in the home. Okay, you try in this molecular orbital, and you can put it and you can try for all other metallocines. So this is how you can do it. If you go to textbook and all, it becomes very difficult to make understand this all the things. Nothing is like that. So you go with this type of mechanism, and this is the important now. So here is the electron going to fill. Other things, the electrons are filled because of the ligands and everything. So you concentrate on this here. So okay, so you can fill here 1 2 3 4 5. So in this one you have to fill all the electrons, and you have to see if it is left one electron, then paramagnetic. If everything is filled, then it is diamagnetic. So this is how you have to generate the molecular orbital diagram of any of metallocines. Okay, simple way. You try in the as a homework, you can do it for all the this one. Now if I want to generate, now if I want to go for the how molecular orbital overlap here, so see for metallocene, if I take this one like this, okay, and I will take it here also. So if I take it here in like this, okay, and if I generate the psi1 here, so simple, if I generate the psi1 here also and here also, what does this psi1 do? That means you know that all are positive sign here. This also positive, this also positive here, this also positive, this also positive, and this also positive. Here also same thing. Now it comes positive, here also positive, plus and plus, like this. So all the sign, all the side there will be a plus sign. Now if I want, now here metal is there, so you have to draw here. So I will write here like this, like this. I will put here metal like this. Okay, so metal. So if I put the metal here in this way, these are the axes here like this. So metal, you have to put this in the middle here. Okay, so you can put this little bit different here, you can put this, and in middle you can fix this metal here, which is this, as I said, that is a dz square. Okay, z square orbital. Now this also being the plus sign, so it is going to overlap here like this. This is, if I go take this here like this and fix it here in between, so this and in between, draw this way only, this also up comes, so both it will fix it here like this. Or if you put this here, it will fix to plus and plus like this, plus and plus like this. So exactly it will fix here like this. Okay, so that way you have to fix it here. So that why this becomes the exact orbital of metal to fix into this metallocene. So like this we can do it. But if I take it opposite now, so what opposite means, what, psi1 and minus psi1 here, that means what now? So if I take it opposite, psi1 and minus psi1 means what now? So here I will draw it here like this. Okay, and here also somewhat I will draw in this way only. Oh, you can draw, you can do it somewhere like this. So here I will take it a plus here, plus 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 plus. So all plus means what? This is psi1. Now I will take here minus here. So this is minus, this is minus, this is minus. Okay, so this is minus. Okay, and this is minus. Now this is minus psi1. See, opposite I have taken, down plus and up minus. Here both plus plus was a down plus, up plus, but here I am taking psi1 minus of psi1. Now here you cannot fix this now. Okay, 3d z square you cannot fix in this here, because here now it has been changed now. So here it was a1g orbital, so you have to overlap with a1g orbital. Now here it is a2u orbital, 2u. See here u, because of what? Not grade, no symmetry is there. A2u orbital is there. Now for A2u ungarade, so you have to go for ungarade only, and that is what the best is, that PZ orbital. So PZ orbital is that will be fixed here now. So if you take the PZ orbital in this way, in particular axis here, okay, x y z, now you can fix this PZ orbital here directly to here. Okay, like this, and you can see that that will be proper overlapping for such type of non symmetric ferrocene. So like this, this is how we can explain the uh, overlapping of the orbitals. Okay, so similarly you can try for psi 2, psi 3. Okay, and the combinations you can see there are more stabilized. Okay, by interaction with as I said, dxz, dyz. Okay, or px, py orbitals. This is what. Okay, so dx psi 2 and psi 3, one I have shown you in the behind when explaining. Now this, if you see psi 2, psi 2, so they are very good fitting overlapped with the dxz orbital, dyz orbital, because they lie in the same plane. And also px, py, and px, py, that's orbitals. Okay, px and py, not pz. Pz for this here. So px and py, so these are the best suitable orbitals for psi 2 and psi 3. Okay, so interaction. But if you go for down now, psi 3, psi 4, psi 3, psi 4, psi 5, so interaction is very complicated. Okay, so that complex becomes it becomes very complicated, and that's what x square 3d x square minus y square. So these all things comes in the psi 4, psi 5, and it becomes very very complicated. And some they remain non-bonding. They will not overlap itself. They become non-bonding. So these are the three main important here. Okay. Now, if you see the in ferrocene, as I said, in the from molecular orbital, you can see in ferrocene from molecular orbital behind we have done it. So if you see the all bonding orbital there, okay, bonding orbital we have taken there, and non-bonding orbitals they are exactly filled. They are exactly filled. Okay, I have shown you behind here. So if you see bonding and non-bonding this way, so 1, 2, 3, 4, 5, 6, 7, 8. So exactly filled, all are exactly filled here, and that's why it is very stabilized. So ferrocene we call it as a very stable. Why it is stable? Because both bonding and non-bonding are exactly filled in this ferrocene, diamagnetic in nature, and that's why it's highly stabilized of all the metallocenes. That is your group 8. So you take any group 8 elements, so you can see that whatever the metallocene formed is very stable because of they are satisfying this very good electronic distribution that exactly bonding and non-bonding is going to be filled. But if you see the metallocenes of 9th and 10th group, okay, so such like example, if we go like cobalt, nickel, something like that. So what happens here, so there will be two electrons in the anti-bonding orbitals. Okay, so anti-bonding orbitals, you can see, you can try it in the home. So there will be left two electrons there in the anti-bonding orbitals. You will see that in cyclopentadiene cobalt or cyclopentadiene nickel, you are going to observe this, and that's why they are going to be paramagnetic in nature. Okay, so cobalt and nickel complexes of cyclopentadienyl are more reactive. Why? Because of the paramagnetic in nature, not like ferrocene. They are very reactive. So this is what. And if you see the cobaltocene of 18 electron, 18 electron means what? It has to lose cation, so it has to form what now? Cp2co plus. So this is going to form. So 18, because it will be 19 electron, 2 electron means what? It becomes 19 electron actually, paramagnetic nature, cobalt. So in order to get stability, it has to lose one electron. Okay, so then it becomes cation. So cobaltocene 18, it becomes 18 electron now after cation, after losing one electron, and that becomes very stable now. Okay, so that's why cobaltocene is oxidized easily, so it will give some electron itself get reduced, and that will it form the stable 18 electron. That's what one question they will ask in any of the competitive examinations. And this is what. And if you see the chromosine, that is chromosine or vanadocene, chromosine or vanadocene. Vanadocene means what? Metallocene containing vanadium. Chromosine means what? Metallocene consisting two cyclopentane with chromium. Okay, so if you see this compound, they are also having the fewer electrons than 18 electrons. Okay, so less electron, they are having 18 electron less, okay, so this also you can you have to see that. Okay, so they are having less electron than 18 electrons, and they are also are paramagnetic in nature. They are also very reactive and paramagnetic in nature. Which one? Chromosine and vanadium. Chromium magnets less than 18 electron, I will write like this, and paramagnetic in nature. Okay, and if you see D5 system, that is manganese. Okay, D5 system, you know that they are having no CFSE, crystal field stabilization is not there for D5 system. That is your manganese complexes, and therefore in high spin form, MnCp2, that is manganese cyclopentadiene in high spin. Okay, in high spin form, you can see that they are very reactive and strongly ionic connector. They are highly reactive, strongly reactive. They are very reactive. They are very reactive and ionic in character. They are ionic in character. This is what about the metallocenes. Okay, so this, I think this is enough for this today's class. So you draw this all diagram in the home and put the molecular orbitals of everything, and put this molecular orbital diagram also, and fill all the electrons for ferrocene, chromosine in the home, and try for this, and keep it ready. So in the Monday Zoom video we will meet and we will discuss more on this. Okay, hope you understood this. In the next class we'll learn regarding the next more concepts, if it's left over by for the cyclopentadienyl. Thank you.